Coming to the grand finale for the day before the party. Oh, sorry, the grand finale is the party. Sorry, Ellie. But our last speaker for the day is Elle. She comes, everyone's seen this cute Micah running around everywhere there. The youngest member of ThoughtBot, there she is. And if she has a nice, cute little ThoughtBot t-shirt, it's because she used to work in ThoughtBot earlier. She's currently working for Blackmill. She is a super mom, right? You're balancing work life in a perfect way, traveling, talking, encouraging people, and that's what we're all here to hear about. So let's learn about the algorithms that Elle has to share with us. Over to you.
Hi. So I know that usually, many people are afraid of algorithms because they think that's too much mathematical knowledge that you need to know. So we're going to go over a few algorithms now without all the mathematical mumbo-jumbo that we have. So today I want to talk about algorithm to live by and why should we care. Now, algorithm is a list of instructions for accomplishing a task. We follow algorithms every day when it comes to activities like getting to work, like cooking a meal that we follow instructions, or, for example, baking bread. Now, I love baking bread, and I find that quite a few developers like that as well. I think the developers find baking bread so appealing just because exactly that it's a function of 5 or 6 things, which is flour, water, yeast, salt, and you also include time and temperature in that. But you can mix them in so many different ways to get your final product. I made that 2 weeks ago. Algorithms, thank you. Algorithms used with computers or in mathematics must be very detailed, and they need to resolve the ambiguities that we take for granted in everyday life. For example, if I ask you to make me a sandwich, there are so many different ways that you can make a sandwich for me. But when you ask a computer to make a sandwich, that you need to be a lot more specific. You need to say, grab the bread that is over there, slice 2 pieces of bread, put butter on that, and continue on with really, really small steps. Another thing about algorithms is that they need to be very efficient, and we always have a search for perfection. They embody the search for efficiency and perfections at the same time. Basically, the 2 most important criteria for an algorithm is that it solves the problem that you're trying to solve and that it does so efficiently. The question is how do we balance those 2 things together and know when to stop when a program is just good enough rather than perfect? Now, we have algorithms not only online. One of the non-web users of algorithms, for example, is in traffic control systems. It is estimated that intelligent traffic control systems can save billions of dollars a year by reducing the idling time at the lights and lowering fuel consumption. Traffic control systems are based on dynamic programming algorithms that consider the time needed for a car to go through a string of lights to get to its destinations, what we usually call the green wave. Everyday algorithms we have different types of them. For example, we have some that are learned, like arithmetics. We have some that we figure out ourselves, like looking up a dictionary definition or looking up somebody in a phone book, if those exist anymore. Or following written instructions, for example, recipes, driving instructions, and everybody's favorite, assembling IKEA furniture. We can define an algorithm in 1 sentence, a precise, systematic method for producing a specified result. Now, why do we care about algorithms? Why should we care? So they help us untangle very human questions and give us strategies for how to live our lives. Algorithms can explain how to have better hunches, how to deal with overwhelming choices, and when not to overthink a decision. They help us to deal with unknowns, incomplete information, and unforeseeable future. They can help us with finding a partner or with the shortest path to a destination. So in this talk, I want to cover 7 or 8 different algorithms and some solutions that we can use to solve them. Let's start with the first one. Usually, everybody talks about binary search. So let's cover that one straight off the bat. So suppose we want to search for a word in a dictionary, for example, the word ruby. We will probably start somewhere in the middle rather than at the beginning of the dictionary and then adjust depending on where we landed. Binary search is an algorithm that takes an input of a sorted list of elements. If an element that we are looking for is in that list, the search will return the position where the element exists, located, or otherwise it will return null. Let's play a game. Let's say that I'm thinking of a number between 1 to 100, and that you are trying to guess the number in the fewest tries possible. Now, with every guess, I will tell you if you're too low, too high, or just right. If we start by just guessing if we start with 1, I will say too low, and then go to 2, I will say still too low, and 3 too low, and 4 too low, and this is not very efficient. So we're going to have to try a lot of guesses before we get to the one that I'm actually thinking of. Let's try a different approach. Let's say that we will start by guessing that the number is 50, and I will say, no, too low. By one guess, we eliminated 50% of the options that we have. So let's try it again, but this time between 51 to 100, the next number that we'll guess will be 75. This time I will say, hey, this is too high. So again, we eliminated half of the numbers that we need to guess. And we can continue with that on and on. Basically, if we started with 100 numbers, our first guess will take us down to 50 guesses. The next one will eliminate 25 guesses. The next one 13. Then we go down to 7, 4, 2, till we get to the number that I'm actually thinking of. So we reached the number that I'm thinking of in 7 steps. If we take the number from 100 to 1,000, but we follow the same process, we will go, again, every time by 50%, we'll go from 1,000 to 500 to 250, 125, 63, and on, and it will take us about 10 steps. If we take that up a notch again, and we'll go up to 100,000, we will get to the answer in 17 steps. So this is basically, if you follow that, a binary log or a log base 2 of 100,000, which gives us 17. So what is that exactly? Let's look at it from the other side. Let's say that 2 to the power of 2 is 4, to the power of 3 is 8, to the power of 4 is 16, and we should all be familiar with those numbers, 32, 64, and so on. If we switch that around, and this time we will say that the binary logarithm of 4 is 2, the binary logarithm of 8 is 3, of 100 is 6.6, which gives us 7 steps. Of 100,000, it's 16.6, which gave us 17 steps. So really, the larger the number, the pool of numbers that we are looking for, binary search helps us find the number a lot quicker. The thing to remember about binary search, though, that it only works when our list is sorted. It will not work if it's not. Next topic, optimal stopping. Let's assume that we are looking for a new place to live. And let's assume, for the sake of simplicity, that we only care about maximizing our chances of getting the very best apartment available. How do we know that the apartment that we are looking at is indeed the best one that we can have, unless we have some kind of a baseline to compare it with? And how do we establish that baseline unless we look at some other apartments and then possibly lose some of the apartments that we looked at? The more information that we gather, the better we will know the right opportunity when we see it. But it is also more likely that we might have missed it already. So what can we do? How can we make an informed decision when the very act of getting informed jeopardizes our outcome? We can take that example to looking for a significant other. Almost exactly. So when practicing serial monogamy, we are faced with a fundamental problem. When have we met enough people to know that we've met our best match? And exactly the same problem as before. What if acquiring that knowledge cost us that very match itself? So in any optimal stopping problems, the crucial dilemma is not which option to pick, but how many options to even consider before making a decision. This problem was introduced in the 50s in something that was called the secretary problem. And the problem is as follows. So let's say we are interviewing for a secretary position, and our goal is to maximize the chances of hiring the single best applicant in the pool of applicants that we have. Now, in our search for secretary, there are two ways that we can fail. We can fail by stopping too early, thus leaving the best applicants undiscovered, or stopping too late, and then hold out for better applicants, which doesn't exist. The optimal strategy clearly requires finding the right balance between looking too much and not enough. Well, the optimal solution also takes the form of what we call look and then leap rule. We set a predetermined amount of time for looking, that is exploring our options and not committing to any of the options, just gathering data. And then we don't make a decision, no matter how impressive a person is. And then, once we get to that point, we enter the leap phase. So we prepare to instantly commit to anyone who outshines the best applicants we saw in the look phase. The magic number that we are looking for is 37%. So the research says that we should be looking for 37% of our time and then be ready to leap. So 37 is our magic number. As it turns out, following this advice ultimately gives us a 37% chance of finding the best option. That changes if we have full information. Let's say that we're trying to pick a secretary, but this time we decide to pick the secretary based on speed type, on type speed. And thus we have a threshold to decide. Then we don't have to look for a certain amount of time. The minute we find somebody that meets our threshold, we can just hire them straight away. So in an optimal stopping problems, when we don't know all the options, optimal stopping tells us when to stop and make a decision. Next problem. Let's say we are digging at grandma's attic and we are looking for a diary. And grandma tells us that the diary that we are looking for is this one box. And when we open the box, it contains more boxes in it. And we can think of a few ways that we can solve this problem. For example, we can make a pile of boxes. While the pile is not empty, we grab a box. Then if we find a box, then we add it to the pile of boxes, and we go back to the pile and we start again. If when we grab a box, we find a diary, that's cool, we are done. This is one way of solving the problem with all our each loops that we have. We can solve it in a different way. So we can go through each item in the box, and if we find a box, we start again. Find and go through the box, and if we find another box, and we start again. If we do find a diary, then we are done. This is what we call recursion. Recursion is a method that calls on itself. It can be applied whenever a problem can be solved by dividing it into smaller problems, and then we can use the same algorithms on the smaller parts. Think of a Russian doll. So each time we open a doll, a smaller one will be inside, and then we repeat the process. A recursive method calls on itself again and again, which makes it easy to write a method that ends up in an infinite loop. Therefore, we need to tell it when to stop. If we look at an example, it's easier to understand if we look at an example. If we look at factorial example, we have a case, which is the recursive case, where it calls on itself. And then we have the base case, where we tell it to stop, where the function doesn't call on itself anymore. In this example, we have, if we call factorial 4, it will call 4 times a factorial of 3. Factorial 3 will call 3 and then a factorial of 2. And factorial 2 will call, again, 2 with a factorial on 1, and then 1 will just return itself. So we get a 4 times 3 times 2 times 1, which gives us 24. Things to take away from recursion. Recursion can be applied whenever a problem can be solved by dividing it into smaller problems, and that you always need to have a recursion case and a base case. Sorting, everyone's favorite. Let's look at the problem of sorting a bookshelf. So imagine we want to alphabetize an unsorted collection of books. A natural approach would be just to scan across the shelf, looking for out-of-order pairs of books, for example, Tolkien followed by Adams, and then flipping them around. Put Adams in front of Tolkien and then start from the beginning. Whenever we make a complete pass on the shelf that we don't need to switch any of the books, then we're done. This is called a bubble sort, and it's not very efficient. So let's try a different sorting algorithm. The next one, this time, we will pull all the books out of the shelf. And then we'll start by pulling one out and putting that on the shelf, and then taking the next one and comparing it to the one that we have and putting either to the right or to the left. And then picking the third one, then decide where to tuck it in. Repeating the process gradually, all the books would end up sorted on the shelf, and we call this one insertion sort. It is slightly better, but it's still not a winner. So shall we try again? Merge sort. In this case, we pull all the books off the shelf and we divide them into 2 stacks. We sort each one the way we've done previously, and it will be a bit quicker because our stack is smaller. And once we have 2 sorted stacks, we just compare the top 2 and decide which one to put on top of the other, and then continue with the ones next. So simply just comparing the top of the stacks. This is called a merge sort. But I want to introduce one last one, which is called quick sort. And again, we're going to use the divide and conquer strategy. So if we are looking at arrays, if we have an empty array or if we have an array of one element, we don't need to sort them, that's obvious. So an empty array or an array with just element will be a base case in an example of recursion. So now we can just return those arrays as is. If we have an array of 2 elements, then we can just compare the 2 elements and then return that. But let's say if we have a bigger array, more than 2 elements. In that case, we need to pick a pivot. So in our example, we picked 3, the first element, but ended up to be in the middle. And then we are going to divide the rest of the elements that we have either below it or above it. So we're going to have a partition with 2 arrays on each side, but those 2 arrays are still not sorted. But if they were sorted, we can very easily just say that we can take the left array plus the pivot plus the right array to give us a sorted list. So we can just run exactly the same algorithm on the 2 sorted lists. So we're pretty much using recursion here to solve our problem. So in this case, once they're sorted, all we have to do is just add them together to get a sorted array. The question is with sorting is, should we be sorting at all? Once again, we should consider the balance between sorting and searching. How much effort does it take to sort out our inbox versus searching through it later? And a sorted bookshelf might not be an everyday preoccupation, but our inbox is most certainly is. And it is a domain where searching beats sorting very easily. Emails can be searched much more efficiently than physical objects. Something to think about. Getting things done. We all have our ways of how to get our things done, our tasks done. So assuming we have a backlog of things that we want to get done, and how do we decide what to do and in what order? We always manage to find some ways to order the things that we do in our days. Currently, I'm trialing out a system that's called a bullet journal and see how I go. But generally, we do not consider ourselves particularly good at doing that. Hence, all the time management guides that we see in bookstores all the time. There is a lot of guidance in all those books, but they're usually inconsistent. For example, the Getting Things Done our system advocates a policy of immediately doing any tasks of 2 minutes or less as soon as it comes to my mind. A different advice is to begin with the most difficult tasks first and then move on to simpler ones. Another approach suggests scheduling fun things first and filling in the gaps with work. And while others makes the case for waiting and deliberately not doing things just right away, just like Avdi mentioned in his talk. So everybody has a different system, and it's hard to know who to listen to. But the first thing that we need to think about when we think about list of things to do is that we need to make our goals explicit. It will make it easier to decide Especially in single machine schedulings, we need to make our goals explicit because we cannot declare some schedule a winner over another one until we know how to keep score. So before we make a plan, we need to define a metric or a strategy. So let's look at one strategy. One strategy, we can say earliest due date. So thus, if we are concerned with minimizing being late, we will pick the one that's due first and do that first. So the best strategy for that is to start with the task due soonest and work back towards the task that is due last. Like homework. There is a different strategy, Moore's algorithms, which in this case, let's look at a stack of foods that we want to use without spoiling them. So Moore's algorithm says that if we start out just like before by scheduling out our produce in order of spoilage date, earliest first, and then one item at a time, and then work through them. However, as soon as it looks like we won't get to eat the next item in time, we pause and then review our meal plans and throw out the biggest item, that is the one that will take the most days to consume, and then continue with the system. So for instance, it might mean forgoing the watermelon that will take us half a dozen servings to eat and just get rid of that and keep on with the rest of the food in the fridge. Not even attempting it will mean getting to everything that follows a lot sooner. The shortest processing time. Maybe due dates are not a concern for us, but we just want to get stuff done as quickly as possible, considering that we cannot change how long it takes us to do some things. Let's consider each of these tasks as a waiting client. Then there is a way to take up as much or as little of our client collective time as possible. For example, if we have a work week starting on a Monday morning and we have a 4-day project and a 1-day project on our agenda, if we start with a 4-day project, and we finish that on a Thursday, our first client will wait 4 days to get it done. And then we'll finish a small project on a Friday afternoon, which means our second client will wait 5 days to get it done, which gives us a total of 9 waiting days. But if we flip that around instead, so if we did the small project first, our first client will only wait 1 day. And then our second client will get delivered his project on a Friday, which will take 5 days. So instead of 9 days, we get 6 days of waiting for our clients. So it's still a full work week for us either way, but now we saved our clients 3 days of their combined time. Something to think about. Schedulist theorists call this metric the sum of completion times. Minimizing the sum of completion times leads to a very simple optimal algorithms called shortest processing time. Always do the quickest task you can first. Shortest processing time reduces the number of outstanding tasks as quickly as possible, which reduces our mental load as well. It is like focusing above all on reducing the length of our to-do list. Cool. Suppose we want to find a magician in our network of friends. And in this case, in order to solve this problem, we need a graph. A graph models a set of connections and how things are connected to one another. It is made from nodes and edges. A node can be directly connected to another node with an edge. So if you look at an example, if this is me at the top, and I look at my connections, I'm connected to Hannah, Caleb, and Lachlan, which are connected, again, to other people. Really, who I'm looking for is Keith. Keith Pitt is a Rubyist from Australia who in 2007 won Young Magician of the Year. In RubyConf EU 2014, Keith made his wallet go up in flames on stage to prove a point. But anyhow, let's say we are looking for Keith. So these are my first-degree connections. Those are my second-degree connections. And we usually prefer first-degree connections to second-degree connections, and then second-degree connections to third one, and so on. This search radiates out from our starting point, and we'll check out first-degree connections first, and then second-degree connections after we exhausted our first ones. We can model that in a hash to define a graph. So in this case, you can see all my connections, and then you can see, so you can see my second-degree connections and who they're connected to, and so on. And it will search in order, and it will add the new ones that it finds to the end of the list. So breadth-first search works only when we search in the same order in which people or nodes were added to our list. Which brings us to a similar problem, which is called a traveling salesperson, which is in some way very similar. In this problem, a traveling salesperson needs to go through a set of cities or towns, but they are not allowed to go through the same town twice. And he can go through various ways. So he can go this way, or they can go this way, or they can go that way. And we need to find the shortest, quickest way for them to go through to reach all those towns. So in these problems, if we allow for the travel person to backtrack, i.e. going through the same point again, then we make it easier to work out a solution. It might not be an optimal solution, but if we are willing to accept solutions that are close enough, and then finding a solution becomes heaps easier to find. So the idea to take from that is just relax. Using constraint relaxations, we remove some of the problem's constraints that we have, and we set about to solve the problem that we wish we had. Once we made some progress, then we try to add some of the constraints back. I've got two more. K-nearest neighbors. So let's suppose that we are Netflix, and we want to recommend movies to our users. And we can plot each user. Again, we're going to use a graph, and we're going to plot each of our users on a graph to calculate the closest nearby users. These users are plotted by similarity, so users with similar taste are plotted closer together. To find the distance between 2 points, we can use Pythagoras to help us. So in this case, we need to find the distance between A and B. We need the locations of x1 and x2, and we need the location of y1 and y2. In this case, a1 and a2. Sorry, yeah, on x and y, sorry. So in our case, for a and b, that will translate to those numbers, which can translate to those numbers, which again, we summarize, and we get that the distance between A and B is 2.236. If we do the exact same exercise with B and C, which we can see with our eyes that are further away, but we just do that in numbers, we get that, yes, they are further away. Now, if we take that same thinking and use that with movie ratings on Netflix, we can see that, for example, both Hannah and Caleb have similar tastes. They both like comedy and action, whereas Lachlan really prefers drama and romance. But let's try and use the same formula to find the distance between all those things. And again, a mathematician in this case would say that instead of calculating the distance in 2 dimensions, we are now calculating the distance in 5 dimensions. But the distance formula remains exactly the same. So if we try and find the distance between the tastes for Hannah and Caleb, our formula will look like something like that, which is pretty much a difference between the 2 numbers, which gives us a difference of 2.64. And if we do the same for Hannah and Lachlan, we get another number which is higher, which means that we really want to find the people that are closer to Hannah in taste, whereas the closest in lowest number, to be able to know which movies to recommend to Hannah, because we know they're going to have the similar taste. So K-nearest neighbors use feature extractions, which means converting an item into a list of numbers that then you can compare them on. Thinking less. When Charles Darwin was trying to decide whether he should propose to his cousin Emma Wedgwood, he got out a pencil and paper and weighed every possible consequence. In favor of marriage, he listed children, companionship, and the charms of music and female chit-chat. Against marriage, he listed the terrible loss of time, lack of freedom to go where he wished, the burden of visiting relatives, the expense and anxiety provoked by children, and the concern that perhaps my wife won't like London. And having less money, of course, and having less money to spend on books. Reasonable. Weighing one column against the other produced a margin of victory, and at the bottom, Darwin scrolled, Mary, 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 QED, quod erat demonstratum, or the mathematical sign of the Darwin itself, then restated in English, it is been proved necessary to marry. Obviously. So when we think about thinking, it's easy to assume that more is better, that we will make a better decision the more pros and cons we can list. The question of how hard to think and how many factors to consider is the problem we call overfitting. And dealing with that problem reveals that there's a wisdom to thinking less. The problem with having too many facts is that they add noise or erroneous data. Stephen Krug, when talking about user testing, reckons that a few tests in each run are better than too many. The more user testing that you do, the more noise you get, whereas with a few tests, you get the most pressing problems that you have with a website. Ocker's razor principle suggests that all things being equal, the simplest possible hypothesis is probably the correct one, instead of trying to complicate things. So strategies to deal with overthinking can be introduce regularization. For example, limit the pros and cons that you can list. There is an example in a retro style that I do that sometimes you have to limit people to 2 points for happies and 2 points for sads, which are the two most pressing things that they can think of. Attach weight for each one of your points and mark them off accordingly. So only the factors that have the big impact on the results remain in the equation. And early stopping. The more time to think, the more complexity we introduce. So giving ourselves more time to decide about something does not necessarily mean that we're going to make a better decision. But it does guarantee that we will end up considering more factors, more hypotheticals, more pros and cons, and thus risk overthinking. And last one, stay away from finer details. Do you know when we do sketching ideas for wireframes, we usually should use Sharpies so we can avoid being caught up on the fine details of our wireframes. Basically, in our case, less is more. Going back to Charles Darwin, when he decided whether to propose, could probably have been resolved based on just the first few pros and cons that he identified, with the subsequent ones adding to the time and anxiety expended on the decision, without necessarily aiding its resolution, and in all likelihood impeding it. What seemed to make up his mind was the thought that it is intolerable to think of spending one's whole life like an utopia, working, and nothing at all. Children and companionships, the very first point Darwin mentioned, were precisely those that ultimately swayed him in favor of marriage. His book budget was a distraction. I want to finish with talking about when algorithms go wrong. On April 9th, 2017, United Airlines Flight 3411 was preparing to take off from Chicago when flight attendants discovered that the plane was overbooked. They tried to get volunteers to give up their seats with promises of travel vouchers and hotel accommodations, but not enough people were willing to get off the flight. So United ended up calling some airport security officers who boarded the plane and forcibly removed a passenger named Dr. David Dow. The officers ripped Dow out of his seat and carried him down the aisle of the airplane. How did he end up being the unlucky passenger? An algorithm that looked at the cost of the ticket, time checked in, was he part of a reward systems and other factors, decided that Dr. Dow was one of the least valuable customers on the flight at that time. Kathy O'Neill says that every algorithm reflects the subjective choices of its human designer, which doesn't necessarily make them bad. How should we address poorly designed algorithms? Well, things that we can do is make them transparent, how decisions were made, and then pay attention to the people the algorithm fails and what demographics are most negatively affected by them. Just something to think about. And that's it. That's it for me. Thank you so much.
All right. Thank you so much, Ali. It was entertaining.